So let's talk about continental drift evidence. That's our topic for this screencast. I'm making this because I literally looked for videos and every one of them was made by a geologist and they're too dry for my taste, which means that you would find them incredibly boring, I had to bet. Let's try me more exciting. So who are we talking about here with continental drift? Well, we're talking about Wegener, okay? Alfred Wegener comes up with this hypothesis of continental drift or plate tectonics, how the continents move, right? He is a meteorologist. He's studying Arctic climates and ice data, and he's noticing ice drifts start to fit together, that a piece of ice breaks apart and the two puzzle pieces swirl around and can fit together. He thinks about the continents and how they could have fit together, right? And he starts coming up with some more evidence that goes with it. So let's look at his evidence. Now, fossils, right? The same plants and animals can be found in areas the continents once have been connected. The Mesosaur is in South America and Africa, and he notices that they're only located in those two places. Climatic evidence up here, right? This is where I'm at now. What that is he's finding things that don't belong where they should be. All right, palm trees in the Arctic, that sort of thing. Fossils of them. Evidence of rock formations. Okay, meaning that rocks look exactly the same with an ocean in between them. And finally, the obvious one, the continental shape. Okay, the continents look like they should fit together. Okay, so come on, me. There we go. Let's look at these. All right, so here's that Mesosaur, right? It is only found right here, right? Nowhere else in the world. All right, and literally you find them on the coast of Africa here, and then the coast of South America there. All right, and the same for all of these. Glosteris, I think is how you say that. It's located across all of these like this, okay? As you look at these, they're only found in these areas. So it's kind of weird that you have an animal found in India, India, and India, Antarctica, and Africa, right? That's a lot of ocean in between those areas. So this is where we're starting to notice this first idea of fossil evidence, all right? Now, rock formation. The Appalachian Mountains right here, right? The rocks in them seem to line up with the mountains in the British Isles and the Caledonian Mountains in Scandinavia. So if you look across these like this, everything seems to be the exact same, okay? Well, it tends to make you think that they were connected in some sort of form at one time or another. So that's evidence number 2 that he comes up with. 3, paleoclimate. This is what we're talking about here. We have tropical things found here in Antarctica, India, Australia, South America. The climate looks different than it does now. I know we think of a lot of these places as very warm, but on the southern edges here, you shouldn't find as many tropical things as the northern edges. One of the other things that we start to see is things like coal. We have coal here. Coal is the remnant of tropical plants. We don't have tropical plants in Maryland, okay? So a lot of these things tend to speak of climates that used to be. Areas in the middle or in more tropic areas, we find evidence that glaciers scraped the ground. Okay, so paleo meaning old, right? Climate, we're starting to notice the old climate doesn't match what's there now, meaning the continents had to have moved. All right, and finally, the continental shape. I think we've all done this little activity before, right? All right, but this is the one you might not know of as much. When they break up into Gondwanaland and Laurasia, this is going to come in to be very important here in a little bit, meaning that, yes, the continents fit together this way, but then we also kind of noticed they started to form 2 different pieces, with North America, Europe, and Asia up here, South America, Africa, Antarctica, India, and Australia here. I'll get it by the end of this thing. All right, so let's look at Wegener, right? What's his legacy? Well, he's missing this main piece, all right? And it's the mechanism or how the continents move. So he comes up with the idea the continents moved. Great. How? I don't know. Not so good. He publishes his work. He puts a book together. He is a joke his entire life, which is sad because he does contribute a great amount. And he dies on an Arctic meteorological expedition on his 50th birthday. Right? Wanders off into the ice, never seen again. Finally, we get to that's about the 30s. Harry Hess comes along in the 50s. He's a geology professor and he's in the Navy at World War II. What a lucky coincidence, right? Geology professor has access to something called a depth sounder on a boat, all right? And as he's traveling across the Atlantic back and forth, he's just looking at readings. Why? Because he's a weird science person that likes that sort of thing, right? He likes getting data and evidence put together, which is great because he starts gathering this data and then continues to after the war, going out and finds all these different things. Up till the 50s, when we started using depth sounders in World War II, we thought the ocean was just deep and flat pretty much the entire way along. But he finds this mountain range, right, in the middle of the Atlantic, gathers some rock samples and stuff like that, and comes up with this idea of seafloor spreading, or that the ocean is moving apart. Okay? He doesn't know where the old stuff is going, though, meaning that, great, the seafloor is spreading, but is the Earth growing bigger? No. We know for a fact that's not true. So where's the old seafloor going? I don't know. So that's something we have to live with for a while until Marie Tharp comes along. She's the first person that accurately maps the ocean floor of the entire Earth, meaning that we didn't know what the oceans look like. She builds off of Hess's work and compiles the data from many other scientists that come together and comes up with the first entire world map, we would call it, right? The bottom of the ocean, the top of the mountains, everything shown, right? And then she shows that there's not only mid-ocean ridges, but trenches as well and subduction zones. So now we start to see that idea that when the plates come together, right, at the other spot, part of the crust goes down and under, and the volcanoes are formed up above it. All right. So that is the next big piece of evidence that comes into play. But we keep getting more evidence, and I'll move on over here. Paleomagnetism, meaning paleo, again, meaning old, right? Magnetism, meaning magnetic data. We start to realize that every few years, right, which is we're possibly in the middle of one of these right now, the magnetic poles reverse. And there's evidence of it in the rocks. So as we look here, we can see this striping along the mid-Atlantic ridge. So this matches up with this idea that the seafloor is spreading this way, right? Because this right here is the same age as this over here based on the striping, okay? And we end up with carbon dating and things like that too that back this up when we actually start to date the rocks. Now, hotspots. We start to learn what these are as well, and this lends us to more movement of continental plates. So here we go. We have a magma that's worked its way up towards the surface, right? And it's a weak spot in the crust. It's an extra hot piece of magma here, weak spot in the crust. As the crust moves over it, it keeps pushing up through here. And we look here, here is the motion of the plate. Sorry. This way is the motion of the plate, like the arrow shows. That we go that way, and this hotspot keeps pushing up new land as it goes, okay? We have the same idea happening in Yellowstone. We have the same idea happening in lots of areas around the world, but these island chains are formed because the plate is moving and new islands are being made here. The ones out here are sinking below the water. These are the biggest ones right here. Earthquakes start to show us these plates, Okay, if we look right here, there's our mid-Atlantic ridge right there. We have earthquake data that shows it. Okay, here's our ring of fire around the Pacific. All right, it's showing us the Pacific plate. Down here, we start noticing earthquakes out in the middle. This is the Nazca plate right here. Okay, and we can start using earthquakes to tell us where these plates are. Okay, or where the boundaries of them are. Biogeographical evidence. And this is where it starts to get interesting too, because we start putting different sciences together. So we start to notice that we have certain evolutionary traits that are only present in certain parts of the world. For instance, flightless birds are found only in what used to be Gondwana land. All right, the one that's not on here, right, is we have penguins in Antarctica, right? But as we look at the top half of the world, right, Europe, Asia, North America, we have no flightless birds, okay? At least not naturally occurring, meaning that they evolved here on their own. All of them take place in the southern hemisphere. It's not a coincidence, and again, these birds don't fly. They're flightless birds, so they're not flying across. Not that any bird could fly across the ocean, but they're not flying across in those sort of ways, okay? How did they get there? They used to live right near each other, and they independently evolved as the continents moved across so that they look different from one another. There's other examples of this. This is probably the most obvious one that you can kind of point to, but it's not only these. Finally, this is one of these that gets us kind of confirming what we believe in this theory, right? We now can put satellites up in geosynchronous orbit, and we can gather evidence of the plates moving, meaning we set points on Earth, and we have the satellites fly over them, loading their location every single day, right? And we notice they move about 1/16 of an inch a year, okay? Not very much, but enough. So meaning this plate is moving in this direction. We take points with it, and we used to have one here, and now it's a little bit more over here, and now it's a little bit more over here. Okay, we're noting how it's moving. So this is new technology we're using, and we're just double checking or reconfirming stuff we've already known. And then we have this idea of the law of uniformitarianism, probably one of the biggest words you'll come across in science, and one of the easiest concepts to understand, meaning that if we have plates moving now, they probably have moved in the past and probably will continue to move in the future, meaning that they didn't automatically, spontaneously start for some reason in the last couple of weeks since we've had, or the last couple of years since we had GPS satellites in the air. It's probably happened for billions of years, okay? And that's one of these things that, like I said, we start to get hung up on, I guess. Uniformitarianism, big word. We're going to look at it again when it comes to things like weathering and erosion. But when we look here, plates moving, right? Measuring, if they've been moving now, they probably have been moving forever. So, what's driving these plates? How are they moving? Well, we use our different data from earthquakes, and we come up with our ideas of the different layers of the Earth. And then we start to notice things about how the waves react in these earthquakes. And here we have these convection cells, right? We notice that we have something like the Mid-Atlantic Ridge here, and we have a convection cell in the mantle, right? We have this principle of convection we've already studied. We know very well, right? And this energy from the heat rising is transferred into the crust. It's driving these plates to move around. And again, the Earth isn't expanding, so we have to have somewhere where it's coming back and down in. And these are what we call subduction zones that are found along trenches. Okay? So, this is the stuff that left Wegener perplexed. He didn't understand this like he thought he would, or like he wanted to in his lifetime. But again, this all comes around in probably the last 60 or 70 years. So for something that you think of and I think of as a concrete piece of knowledge that we've always known and always will know, was not up until very recently. Okay? So that is your evidence of continental drift, Hopefully, I was more interesting than the boring guy I found on the internet.